Hi there. I want to start talking to you about programming. So, if I give you a program like the one on the screen and I ask you, what does this do? Can you tell me? So, pause the video for a sec, think about it, and start it back when you're ready with your answer. So, what does this do? Well, you can see it takes three variables, x, y, and z. Initially, we assign m to be x. Then if m is less than y, we set m to be y. And if m is less than z, then we set m to be z. And then finally, we return m. All right, so what's going on there? Well, if we think of specific numbers, maybe it's helpful. Let's take 1, 2, 3. So if m is initially 1, then here 1 is less than 2, so we'll set m to be 2. Oh, and then if 2 is less than 3, we'll set this to be 3, so we'll return 3. So it seems to be picking the largest number. Indeed, this seems to be the max of 3 numbers. And you can see that this actually works generally, even if they're in a different order. So if I have 1, 3, 2, we'll still be fine, because we'll start off with 1. Then here we'll assign 3, because 3 is bigger than 1. But 2 is not bigger than 3, so we won't execute this statement. So this is actually computing the max. Sort of abstractly, what are we thinking about here? Well, the reasoning, what's actually going on in your head when you think about this program is you start off thinking, well, what is the value of m? M initially is the max just of x. I mean, so it's x. But it's also the max of x. The max of x is just x. And what's happening with each line we execute is we're expanding the scope of the max by one additional variable. So after we've executed line 4, we can see that we've now determined that m is not just the max of x, but it's the max of x and y. And now by taking the max of x and y and comparing that to z, we can determine that on line 7, we have the max of x, y, and z. So all of these things. So that's great. And what's really interesting about this way of thinking about programs is that when you start looking at it this way, really you don't need the code. So what we're doing here is we're initially setting m to be the max of x. Then we set m to be the max of xy. So we're going from max of x to max of xy. We're going from max of xy to max of xyz. And so you can see that the lines of code that I've got in there are simply getting me from one step to the other. So we're establishing the initial premise that m is the max of x. And then knowing that, we can add in y and then correspondingly add in z. And looking at the code in this sort of logical way is actually what your brain is doing when you read code. So if you're actually reading code and genuinely understanding it, then your brain is going through this kind of process. And so being aware of it can be really helpful. So, when we write code, we often want to actually test it. So, I think I just reasoned through this code. I'd like to, I'm convinced that it's correct, but maybe there's a small error, and so it's useful to actually have some tests. So since code is automated, what we can do is we can sort of take this code and we can type it in, and we can sort of see what it does. So I'll just run this and see what the output is. And you can see that it does work. So what I've got here is, in each case, the max is 31. And I'm running 3 different tests for 3 different positions because I want to make sure, that I'm not got some funny little bug. And you can see this kind of test will work. So if I do have a typo, sometimes the code is correct, but, morally correct. But you've got a typo when you entered it, like copy and paste error. This kind of thing is quite common. But what we're doing here is what we call manual testing. So in order to check this, I must visually inspect the output. This is not going to scale. So you can imagine if I have a very large program, checking all these little tests is going to be a big problem. And worse, this kind of testing makes you conservative as a programmer. So, the problem is you run your code, you get it to pass the test. So I'm like, okay, shit, this is not right. I got to get that to be a Z. Now everything's great. Okay, pass the test. And then usually what people do is they don't remember this stuff. They just wipe it out to their test. And they'll just start, proceeding. But now if somebody says, hey, that max function, you could write it a different way. Is that fine? Like, let's say I want to swap these two. I want to put the comparison to Z first. Is that okay? Well, probably. But in the absence of the test, you might be insecure to make this change. So what we say is that the code can become brittle if you have these kind of manual tests. So a better approach is to what we do, what we call automatic testing. So there's a little bit of work here. You can see that there's some stuff I have to write out, but it's in general worth it. So this is not something you probably would have done in your first programming class, because in your first programming class, it's sort of one and done. You write the code, you get it to work, you're done. That's not what we're doing here. So in general, code doesn't work like that. You're usually programming for another programmer. You're writing a program that's going to be around for hopefully many years. And there'll be small changes in maintenance done to the code. And it's important that people be able to develop some confidence that their changes haven't broken anything that you had originally created. So what we'll do is something like this. I'm going to write a test function here called testmax. What testmax does is it takes the values x, y, and z and an expected value. What we're going to do is we're going to run the max function on these parameters x, y, z and see what actually comes out. And we'll check to see if the expected value is equal to the actual value. And if they're the same, well, that's great. We don't need to do anything. Everything was hunky-dory. Otherwise, we need to inform them that the test failed. Right? So in general, passing tests are usually silent because we expect tests to pass. We really only want the squeaky wheel when a test fails. So if you print out stuff for passing tests, you end up with too much noise and it's impossible to tell what's going on. So let's just see what this does here. So when I run this test, you can see, oh, it failed. Why did it fail? I did that intentionally. So this is a failing test. So what it says is here, I was expecting 31, but I actually got 21. And the arguments were 11, 31, 21. So it failed in this case. And just by inspection, I can see what the problem is. There's just a typo there. So if I fix that, then it'll finish the test. This little thing at the end is helpful. If you leave this out, sometimes it's disconcerting because you run the program and you just get silence. Silence is it working? Is it not working? You could have an infinite loop here. So if you just put in some sort of while loop or infinite loop, the program will just hang forever. So you can do something like this. While true, just do nothing. And it's kind of tricky to see the difference between an infinite loop and a passing test. So here you see this little red button here. That's saying that the program is still running. So I can terminate it. But so there you can see the program has terminated now. So you can see that the program does terminate here because it's no longer giving me a red button. We're going to be doing this style of testing in this class because it's relatively light. It doesn't need many tools and stuff. There's a huge amount of frameworks for doing this kind of testing. So you can pick your language, and even for just Java, there's a huge amount of frameworks to do this. The one that I've used in the past is called JUnit. We will use these in later courses at DePaul, in particular in software engineering. We'll talk about using testing frameworks. But for us in this course, it's just extra weight. We're not going to bother with it. So we're just going to write these kind of manual automatic tests. So I'm going to write for your homeworks, you'll find these test functions. You'll find a main program with tests like this. I've written this function here to take three variables, x, y, and z. I could equally have written it to take an array where I'm just going to look at the three elements of an array. So this is how you do this. And to make things just clear, when I use arrays, I'm going to use doubles rather than ints as the kind of the values of the array. And that's because arrays are indexed by integers. So it's nice to have that contrast between the index, which is an int, and the value in the array, which is a double. So here is an array of doubles. And the code here is absolutely unchanged. So here I've got the max of three things, x, y, and z. Of course, this has a bug. That should be y. But what I'm doing here is the same. I'm just calling them a0, a1, and a2. Of course, the way we invoke the function now also changes. Instead of passing three separate parameters, I'm passing a double array. And the way we can instantiate a literal double array in Java looks like this. So here I'm passing in the array with elements 11, 21, and 31. I'm expecting 31 to be the result. So let's see if this still works. Yes. Okay. So, and the same reasoning applies. I'm doing exactly the same thing going through these three elements. Note that we have two statements here which are identical except for the index. So at this point we have a of 1 on one line and a of 2 on another line. And we can get rid of that commonality. You could imagine we did this for a 4-place array. We'd have 4 lines, or 5-place array, we'd have 5 lines. So we can get rid of that redundancy by using a loop. So what we're doing here is we're initially going to execute this line for I is equal to 1. We'll check to see a of 1. And then we'll do it for a of 2. Okay, so we're doing it for 1 and then for 2. And so we're just doing it twice. So this will now execute here where I is 1 and then where I is 2. Note that we will not do it for the case where I is 3, because 3 is not properly less than 3, and therefore this loop will not execute for the value of 3. Again, the syntax here in Java is to pick in a for loop, we say that I is initially 1. We want to increment I by 1 each time, and we're going to stop when this predicate becomes false. So when I is greater than or equal to 3, we'll stop. Okay, and this runs beautifully. What we've got, at this point though, you can see how arbitrary the choice of 3 is. So the number 3 here feels very out of place. Like, why is 3 here? Why are we only dealing with arrays of size 3? That does seem fairly arbitrary. So what we can do instead is work with an array of any length. And we can do that by using the length field of the array classes in Java. So each array has a length associated with it. And so we can just use that length as our bound. So note that if we have an array with 3 elements, the length will be 3, and the indices for those elements will be 0, 1, and 2. So the way we go through them is something like this. We have a of 0. I can then start here at a of 1. This will go up to a of 2. And then again, once I is equal to the length, the loop will not execute. So when this becomes false, so the index is not properly less than the length, we'll exit the loop. So this is sort of a standard way to go from the beginning to the end of an array. And this function works just fine. And you can see now I can actually use different lengths arrays, and they should work out fine. So here I have tests where I'm going to check a 2-element array, check a single element array. No problems. This should all just work fine. And so we can run it. and it should be fine. Yeah, it's all good. The thing that we've written here is still correct. And I think it's important now to look at it again, that we've generalized to an arbitrary length array just to see what we've done, right? So what's happening is that at each step, we're increasing the number of elements we've looked at by 1. So, and we're using a variable to keep track of how far we've gone. So the variable is called I. And what we're doing here is keeping track of the elements from a of 0 up to a of I minus 1. So at each time through this loop, we've looked at all of the elements from a of 0 up to a of I minus 1. So let's see if that's, I'm going to claim that's true. Let's just check it to make sure that I'm saying the truth. So initially, m is a of 0. So when I is 1, have I really looked at max of a of 0 up to a of I minus 1? Well, yeah, this is, in this case, when I is 1, 1 minus 1 is just 0. So I only have to have looked at one element, which I have. Before the loop even starts, I have looked at a of 0. So it holds at the beginning. And then as I make a step, right, let's suppose I've looked at I elements. Is it true that when I increment I only do that after I have looked at the ith element? And in fact, this is what's happening. So assuming that m is the max of, say, the first 3 elements, now if I look at the 4th element, I can then say after the loop has gone around that I've now looked at all 4 elements. So each time through the loop, I'm adding 1 more element. And then the key here is that when I get to the end, of course, I is going to be equal to a dot length. And therefore, this invariant will tell me that m is the max of the elements from a0 up to the length minus 1. And of course, that's all of them. Okay, so that is all of the elements in the array. And therefore, I can safely say that this is really the max. So what we're using here is what's called a loop invariant. This is something that is true every time before we execute the body of the loop. So the body of the loop here is just line 8. And before we execute line 8, this statement is always true. And it's also true when we exit the loop, which is really very nice. And this is what sort of the reasoning. This is actually, if you look at how you read code, you'll find that if you really understand a loop, you're doing this kind of reasoning in your head. There's no way to understand a loop without doing this kind of reasoning, right? So we have to be able to think about what's happening each time around and generalize it into some abstract form so that we can sort of understand what the loop is doing as it progresses. This code is excellent, and it's handled arrays of arbitrary length. But there's one assumption in the code that makes it a bit brittle, which is that we're assuming that the array has at least one element. So in fact, I can try this on an array that has no elements. And what is this code going to do? So first of all, you might wonder, is this valid Java? And you can see that Eclipse is fine with it. So we can execute. And oh, that's not nice. So what we've gotten here is what's called an array index out of bounds exception. One thing that's wonderful about Java is that when you get an exception, it will tell you exactly where that occurred. So you can see what line it happened on. It happened here. And so you can just click that and see. And it'll tell you, actually, the array index out of bounds exception will tell you that index 0 out of bounds for length 0. So indeed, you can see which test failed because we were actually on in the main program on line 24. So it was actually this test that failed. And that makes sense. So the array has length 0. I'm trying to look at the 0th element. That's not okay. Okay, so, and it's obviously nothing to do with the value I chose here. This is just because I'm looking in the array in this way. In this case, we need to check if the length is 0, then we need to do something. So what do we do? Most beginning programmers will think, well, I'll just do something like this. I'll return 0. Okay, whatever. And this is sort of a solution that does get it to pass. In this case, I have a value. But is 0 a good choice here? I mean, it turns out that 0 is just yet another magic number. It's completely arbitrary. And these kind of magic numbers are just bad. You don't want to have them in your code. They're going to make your code brittle. It's going to break in certain cases. So in this case, what we've done is identify the empty array with the array that just contains 0, or in general, any array that contains 0 as its max. I mean, we could have a bunch of negative numbers and then a 0, and then the max is going to be 0. So having that be the value for the empty array seems kind of wrong. In this particular case, there is a value we could use. It's called double dot positive infinity, or sorry, negative infinity is the one I want. So double dot negative infinity. This makes some mathematical sense if you think of the mathematical definition of max. This is an identity value for the max, but there's many cases where this kind of mathematical identity doesn't exist. And so, there's often just not a good choice for what you should do in this case. So, I mean, you could just say, well, screw it, we're going to throw an exception. And Java's already throwing an exception, so we should be fine with that. But this exception is not very informative. It's giving us the wrong information in some sense. So usually what we'll do is to make it clear that we intend this exception to happen, we'll use a different exception. So in this case, I would put in my documentation that the double needs to be non-empty. So we could add a comment here. This double array cannot be empty. And we can also document this by throwing a particular kind of exception. So the common one for this kind of case is an illegal argument exception. So it's saying that the argument A that you gave me is not a good argument. So so we can run it, the code there. So this is an illegal argument exception. And exceptions are very useful. This is what they're essentially for, is these kind of exceptional cases. That's why they're called exceptions. The mechanics of them is not particularly complex, and I don't want you to get too obsessed with all the details of exceptions. But when you want to, the idea here is to throw an exception and then it can be caught by a calling function. So here I am throwing an exception from max, meaning max doesn't have a good return value at this point. And so it throws that out to the outside world. If the outside world is expecting this exception, it can catch it. So this is the way you do this in Java, is with a try catch statement. So I'll try to call max, not sure it's going to work. And here, if it fails, then I'll catch that exception. In this case, I actually want the exception. So here I'm trying to test the code to make sure it behaves the way I expect. So I'm actually expecting the code to throw an illegal argument exception. So that's what I want. So if I catch the illegal argument exception, I just do nothing. Instead, if the code does not throw an illegal argument exception, then I'm going to be upset. That's not what I want. So in particular, let's suppose we return 0 here. Then we'll fail here because I was expecting the illegal argument exception, not some other thing. So this is a failed test.